So we've got the train accelerates uniformly. Uniformly, we'll talk about that in a second. From rest to 72 kilometers per hour in 5 minutes. So I know V. Can you see that the fact that it's going to 72 kilometers per hour means that that's the final speed? So V equals 72 kilometers per hour. Converted that to meters per second by timesing by 1,000 to get to meters, and then, as Marcus suggests, divide by 60 twice. Note, that's how it would, you could put it into the calculator. Gives us 20. Time is 5 minutes. It does that in 5 minutes, so that's delta t. So we can think of it as delta t. 5 minutes, which is 300 seconds. Do we know anything else? U, which is? Good. We know, not explicitly stated, but we know that U equals 0 meters per second, kilometers per hour. It doesn't matter, does it? Starting from rest means that U equals 0. So we do know U, it's 0. What do you think uniformly means? Yeah, the acceleration is constant. In other words, if I were to plot a graph of the acceleration, it would be a straight line, uniform acceleration. So in this case, we do know that the acceleration we come up with in the end is constant, uniform. Okay, so that's what we're given. We've now got it in the right units. We can now determine the displacement. We've got two things to find, the displacement and the acceleration. Okay, so we've got the information after the displacement and the acceleration. Suggestions for a formula that might be useful. So, yeah, to work out the acceleration, that's v minus u over delta t. We know v, we know u, and we know delta t. So we can do it. 20 minus u is 20 over delta t, which is 300. So the acceleration is going to be 20 divided by 300, which is 0.06. Is that rounded? Right, so let's call it 0.067 to two significant figures. And the unit? Meters per second squared to two significant figures. That's the sort of ideal way to leave that answer, because we've rounded it. 0.067 meters per second squared to two significant figures. And then we can use that to find the displacement. Which formula are you going to use for displacement? We could use that. S equals ut plus a half at squared. Yeah. That uses something we found, which is acceleration. Is there a way we could have found the displacement without using something we've calculated? Using the original information, is there a way we could have found the displacement? So we've got, yeah, we can use the formula that displacement, or average velocity, equals displacement over time. In other words, displacement equals average velocity times time. We know the time, and can we find the average velocity? Is there a formula that allows us to find the average velocity? Yes, v average is u plus v over 2. So u is 0, v is 20, so average velocity is 10 meters per second. Times that by time, which is 300 seconds, so s is 3,000 meters. Is that the same as you got the other way? Hopefully. If you don't get exactly that, it's because you've rounded this acceleration, haven't you? Which is the best way to do it. Yeah, because if you'd made a mistake with the acceleration, you would still get the displacement correct, wouldn't you? Because you've used the original information. So there's often more than one way to do this. I'm not saying that using this formula, s equals ut plus half at squared, is wrong. What I am saying is if you can use the original information, then that's better, because even if you got the acceleration wrong, you'll still get the displacement correct. There's often more than one way to do these problems, so don't just pile all the way straight into the first one you see. Just give it a little bit of thought for a second. Is there another way I could do this that maybe is a bit more easier, a bit more elegant, likely to give me a right answer, regardless of what happened in an earlier calculation?